So let's talk about surface integrals, okay? And we'll start with surface integrals of scalar functions. Suppose you have this surface here in orange. And as you can see, it's embedded in space, R3. This is a two-dimensional sheet in the sense that if you live on the sheet, you could only move in 2 dimensions. You don't want to come off the sheet. But it lives in the broader R3 space. And suppose we want to know the mass of this sheet. Okay, suppose we are given the density. Okay, F would have units, say in SI units, or we could just make it more broad, mass over not volume but area. Okay, and so you have the units of surface density there, mass per area, and you want to figure out the total mass of this object. Well, what would you do? You can first try to find out the small mass. Okay, we could find out the little mass, dm, of just a little tiny chunk here, say this chunk right there. dm would be F at that point, okay, specifically at the point where you're interested in, times this ds, the little area of this little piece that you see over there. And then you add up the small masses as you move along the surface S, and you'll end up with the integral, okay? And here we have in light blue, you could see, once I erase this little patch ds, it's the small area of that two-dimensional patch living in 3D. And f, well, I can't really plot f on this, right? F is a function of 3 variables, and so I would have to borrow, say, some sort of color scheme to let you know, for example, if the density is very low here, maybe I'll use blue, and as it gets more dense, I could start using red or vice versa. Okay, that's the only way to represent, or the simplest way to represent a function of 3 variables. Okay, but that's the idea of the surface integral. Okay, and you might have noticed I said, well, once we do the double integral, we're going to move along the surface. Now, how can we move along the surface? We had a similar problem when we did scalar line integrals. With scalar line integrals, we put an ant on the line, and we had r of t. This is for line. Okay, we had r of t is equal to x of t, y of t, basically following the position of a little ant as it moves along the curve. And we called that the parameterization of a curve. Okay, this could have lived in R2 and R3. Well, how do we move along not a curve, not a one-dimensional curve, but a 2D surface? Well, we need the idea of a parameterization, and let's talk about that and look at the parameterizations for different simple things. Here, a parameterization will depend on 2 variables of a surface. Okay, this is of a surface. Parameterization of a surface. Okay, and you could see it doesn't depend on t as it did for a line. That one line is one-dimensional. Here it's 2-dimensional, so it depends on u and v. And you'll have the x component depending on u and v, the y component depending on u and v, and z component depending on u and v. Now we also, for lines, needed to always have bounds for our parameterization. And we also always have to have bounds for our u and v, And these live in the UV plane, okay? It's a completely different plane. It's a two-dimensional plane, but you could think about it as U on the on our traditional x-axis and V on the traditional y-axis. It's one way to think about it. And what a parameterization does is it maps this sheet onto this surface. So this little point here, UV, once we plug it into our parameterization, we'll end up at this vector. Okay, this red vector that you see there, R at UV. And now this whole line in the UV plane, where does that get mapped? Well, it's getting mapped, that blue line there is getting mapped along this blue line here. Okay, and this green line here is getting mapped along this green line. Okay, and you could move around the whole parameterization or the UV plane, and you could see that you'll sweep out the whole surface as you're moving there.